Today, we shall study about most mass energy and nuclear binding energy in nuclei. Mass energy is Einstein showed up from his theory of special relativity that it is necessary to treat mass as another form of energy. Before the advent of this theory of special relativity, it was presumed that mass and energy were conserved separately in a reaction. However, Einstein showed that mass is another form of energy and one can convert mass energy into other forms of energy, say kinetic energy and vice versa. Einstein gave the famous mass energy equivalent relation E barabar mc square, where the energy equivalent of mass m is related by the above equation and c is the velocity of light in vacuum and is approximately equal to 3 × 10 to the power 8 meter per second. Experimental verification of the Einstein mass energy relation has been achieved in the study of nuclear reactions amongst nucleons, nuclei, electrons and other more recently discovered particles. In a reaction, the conservation law of energy states that the initial energy and the final energy are equal provided the energy associated with mass is also included. This concept is important in understanding nuclear masses and the interaction of nuclei with one another. Nuclear binding energy, we have seen that the nucleus is made up of neutrons and protons. Therefore, it may be expected that the mass of the nucleus is equal to the total mass of its individual protons and neutrons. However, the nuclear mass m is found to be always less than this. For example, let us consider O8 to 60, a nucleus which has 8 neutrons, neutron 8 and 8 protons. We have mass of 8 neutron barabar 8 × 1.00866 unit, mass of 8 protons barabar 8 × 1.00727 unit, mass of 8 electrons barabar 8 × 0.0055 unit. Therefore, the expected mass of oxygen from 8 to 60 nucleus barabar 8 × 2.01593 unit, from 16.12744 unit. That being mass of O's 8 to 16 found from mass spectroscopy experiments is seen to be 15.99493 unit. Subtracting the mass of 8 electrons from this, we get the experimental mass of 8 oxygen 8 to 16 nucleus to be a 15.88053 unit. Thus, we find that the mass of the oxygen 8 to 16 nucleus is less than the total mass of its constituent by 0.1369 unit. The difference in mass of the nucleus and its constituents, delta m, is called the mass defect and is given by delta m barabar zmp plus a minus z mn minus m. What is the meaning of mass defect? It is here that the Einstein equivalence of mass and energy plays a role, since the mass of the energy oxygen nucleus is less than that of the sum of the equivalent energy of its constituent. If one wants to break the oxygen nucleus into 8 protons and 8 neutrons, this extra energy delta mc square has to be supplied. This energy required EV is related to the mass defect by EV barabar delta mc square. If a certain number of protons and neutrons are brought together to form a nucleus of a certain charge and mass, an energy EV will be released in the process. The energy EV is called the binding energy of the nucleus. If we separate a nucleus into its nucleons, we would have to supply a total energy equal to EV to those particles. Although we cannot tear apart a nucleus in this way, the nuclear binding energy is still a convenient measure of how well a nucleus is held together. A more useful measure of the binding in between the constituents of the nucleus is the binding energy. per nucleus, EBN, which is the ratio of the bonding energy EB of a nucleus to the number of nucleons A in that nucleus. EBN बराबर EB बटा A. We can think of bonding energy per nucleons as the average energy for nucleon needed to separate a nucleus into its individual nucleons. Figure 1 shows a plot of the bonding energy per nucleon EBN versus the mass number A for a large number of nuclei. We notice the following main features of the plot. The bonding energy per nucleon EBN is practically constant. It means practically independent of the atomic number. For nuclei of middle mass number 30 smaller than A smaller than 170, the curve has a maximum of about 8.75 mega electron volt for A by about 56 and has a value of 7.6 mega electron volt for A about 238. Second, E is a lower for both light nuclei A smaller than 30 and heavy nuclei A is greater than 120. We draw some conclusions from these two observations. The force is attractive and sufficiently strong to produce a bonding energy of a few mega electron volt per nucleon. The constancy of the bonding energy in the range 30 smaller than A smaller than 170 is a consequence of the fact that the nuclear force is short range. The bonding energy per nucleon is constant and it is approximately equal to pk, where p is our number of neighbors in a nucleon within the range of NUC, a force, and k is our constant having the dimension of energy. A very heavy nucleus has lower bonding energy per nucleon compared to that of the nucleus with the lower atomic numbers. It is used in fission for energy production. Fourth, the bonding energy per nucleon of the fused heavier nuclei is more than the bonding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a process of fusion. This is the energy source of the sun. Nuclear force. The observation obtained during 1930 to 50. The nuclear force is much stronger than the Coulomb force acting between charges or gravitational forces between masses. The gravitational force is much weaker than even Coulomb force. The nuclear force between two neutrons falls rapidly to zero as their distance is more than a few femtometer. This leads to saturation of forces in a medium or large size nucleus, which is the reason for the constancy of the bonding energy per nucleon. A rough plot of potential energy between two nucleons as a function of distance. The potential energy is minimum at the distance of RO of about 0.8 FM. This means that force is attractive for longer distance than 0.8 FM and repulsive if they are separated by distance less than 0.8 FM. The nuclear force between neutron, proton, and proton is approximately the same. The nuclear force does not depend on the electric charge. There is no simple mathematical form of the nuclear force.